Okay, water, copper sulfate. Let's decrease the amount of water a bit. All right. Now, when I first pour this copper sulfate into the water,
Nothing.
nada, right? All right. Now, if I start to stir vigorously, what starts to happen to the color of the water? It turns blue. All right. Now, if I keep stirring and stirring and stirring, it gets more and more blue, yes?
Yeah.
All right. Now, does it reach a point where there's still solid on the bottom and it stops getting any more blue?
Mm-hmm.
Sure. Yes. Okay. You get to the point where no more of the solid will dissolve. Right? That's basically all they do. You know, I like this. I'm doing this only because it actually gives you a visual representation of what they keep talking about. All right? You know this. The classic is chocolate milk. If you do chocolate milk powder, like, of course I like Ovaltine, not chocolate milk, but you know, the good British Ovaltine that's made of malt, not sugar, really good. If you ever get a chance, you ought to try it if you like Ovaltine. How many of you like Ovaltine? Okay. All right, anyhow. So anyhow, you take your milk, you dump in your Ovaltine, you get that sludge at the bottom, right? All right? And that sludge is the best part. But anyhow, so what's actually happening, though, are some of the Ovaltine molecules are escaping. And some of the other Ovaltine molecules are going back to being Ovaltine again. You can't see it, but it's in equilibrium. All right? In our case that I just made, we've got the copper sulfates down here as a solid. Then you've got the copper ions and the sulfate ions in the solution. And what's starting to happen is some of those copper sulfates are breaking up, and some of the other coppers and sulfates are getting back together again. We've reached equilibrium. All right? Now, this is just another K. That's all it is. All right? This particular K is called Ksp. Now, the reason it's called the solubility product. All right? Now, just like the last unit, we had Ka had to be written a particular way. It had to be the acid plus water going to the conjugate base plus H3O plus, right? That's the way you write the Ka expression. The Ha is always a reactant. The A is always the product, so you always write it the same way. True? Okay, here's the deal. Same drill with this. The way Ksp is always written is the solid over here and the ions over here. Always. Okay? Now, if you go all the way back to the first K chapter, what goes in the K expression? Ions and gases, right? And dissolved liquids. Dissolved. All right, dissolved liquids. What about solids? No, because if you have some solids, you've got enough solid. So it's the same thing here. We start with solid, we end with ions. So if I'm writing the Ksp expression for this reaction, it's the copper sulfate solid becoming copper ions and sulfate ions. Okay? That's all it is. Now, can we write the Ksp equation for that? So this is the expression, right? What or? Well, this is the reaction. Oh no, you gotta erase. All right, don't use pen in my class. All right. So the equation the Ksp equation is going to look like what? What goes on top? What's always on top on K? Products or reactants? Products. What's on the bottom? Reactants. All right. So what's it going to look like? This K. Concentration of copper times concentration of sulfate. Anything on the bottom?
No.
Nope. Because it's a solid. There it is. That's the Ksp expression. That's all there is to it. That's it. All right? They gave you almost a whole chapter on this. Now watch. It gets a little weirder, but not much. It gets a little weirder, but not much. Let's see. All of that will still be up on the board. Okay, now, here's first step in weirdness. Let's say, instead of copper sulfate, let's use copper hydroxide. This is, if we were naming this properly, it would be copper what hydroxide? What would be the Roman numeral? Hydroxide is what charge?
2.
Hydroxide is what charge?
Minus
-1. 2 of them. -2, so the copper must be
2.
+2. Remember, this is like third day of class? All right, so copper 2 hydroxide. All right, now it just gets slightly weirder. No big deal. Copper hydroxide. It's in equilibrium. We get copper ions. And what? How many hydroxides? 2.
Right.
Everybody okay with that? No magic. Right? Okay, now, what's the Ksp expression? There's nothing on the bottom because that's a solid. So it's going to be concentration of copper, concentration of hydroxide squared. That's no big deal, is it? That's easy. If there's 2 of them, make it squared. We've been doing that for a month and a half. Okay. Ready? Now here's where it gets a little weird. You guys, on the sheet I gave you today. Okay. Copper, hydroxide. Okay, so the Ksp for copper hydroxide is 4.8 times 10 to the -20th. Thank you. All right. Okay, now, think about this. What's going to happen if you throw some copper hydroxide in water? You're going to get a copper, and you're going to get 2 hydroxides. Right? That's no big deal. All right? So, if we call the concentration of copper X, what's the concentration of hydroxide going to be? 2x. Right? Think about that. For every 1 copper that goes in there, if we call the concentration of the coppers X, the concentration of the hydroxide is going to be double that.
Sure.
Does that make sense? For every 1 of these, we're going to get 2 of these. Good so far? Okay. Well, now, if we're going to solve that, we'll take the equation you already came up with, copper, and we want to solve for what the concentrations actually are. Let's plug everything in. 4.8 times 10 to the -20th equals x to the first and okay? Don't let it weird you out that we doubled it and squared it. It doesn't matter. It doesn't matter. All right? You're just counting the number that actually went into the water. So for every one of those, you get 2 of those. So 1x, 2x. Right? Now, is that any big deal to solve algebraically? What's 2x the quantity squared? 4x squared, right? Times x, which is what? 4x cubed equals 4.8 times 10 to the negative 20. Right? Now, everybody's good with the idea, divide by 4 first, take the cube root.
Right.
If you have any trouble with your calculator taking a cube root, the easiest way is to use the little caret, parentheses 1/3. Easy way to take a cube root. Okay? Does that make sense? So, I don't know what that would be. That would be 1.2 times 10 to the negative 20th, cube root of that, whatever that is. Point is, I don't need the number. The point is, what would be the whatever that is, what would be the concentration of hydroxide? Twice that. You see it? Okay. So one way to do KSP problems is to just throw the stuff into water. Okay. Now, can I throw you one more thing? I want to throw a couple things in just into play, get them started, start to plant seeds. All right? Now, at some of your houses, you have a water softener. Okay? Water softener. It's full of salt. Right? Just plain old sodium chloride. The reason you have that water softener in there is because that chlorine grabs a hold of metal ions and makes insoluble solids. So it takes those metal ions out of the solution. The biggest thing around here is calcium, which makes you what's called hard water. Some people have problems with copper ions in their solutions. All right, if it's really bad, you've got lead. That's not a good thing. All right, but it is possible. All right, so what we then do is we can do this. We can pour together 2 solutions and ask if it precipitates. We're going to take it the other way. In this case, we said if we put copper hydroxide into water, right, some of it's going to break up, some of it won't, if we have enough to reach saturation. Sure. Okay? In this case, what I'm going to say is we've got, say, sodium chloride, so we've got chlorine ions, and the sodium can go hang, all right? And then we've got some kind of thing with, say, copper ions, and we don't want to drink copper, not in large quantities. So we're going to mix them together and see if they precipitate. So we'll add some chlorine and some copper and see if we get copper chloride solid. All right, how would we test that? We have to see if it reaches the KSP. The KSP is the limit. Just like, remember when we did Q? This is the same drill. We're going to do a Q. We're going to say, okay, what's the concentration? So what would be the K expression for copper chloride? What are the things in copper chloride? Copper and chlorine, 2 of them, squared. Okay, so another way we can do this is we can say, okay, once we mix them together, what's the concentration of copper? What's the concentration of chlorine? We can do it as a Q. We can say, okay, Q equals, same exact thing. We plug them in, is Q bigger or less than KSP? Just like we did before, is Q bigger or smaller than K? Right. If Q is bigger than K, we have too much product. So we move to reactant. Remember that? Same thing, nothing new. All right, so here's the drill. What's the reactant in this case? It's the solid.
Right.
So if Q is bigger than Ksp, we're gonna move back to solid, so we're gonna start to precipitate. If Q is smaller, we don't get any precipitate. See it? That's it. That's all there is. That's Ksp. All right? Now, are we gonna mess around with it? Then we'll get into let's let the common ion thing sit for a day. I'll plant a seed with that tomorrow. Okay? So this is the beginnings. It's not that bad as long as you just think of it as, I gotta write, I've gotta write the Ksp always the same way. It's gotta be the solid on one side, the ions on the other. As long as you remember that, you remember that the reactant is a solid, so it's not in the K expression, then you just write the Ksp with the ions. Then you remember if there are 2 of them or 3 of them, you just have to square or cube it. Okay? But then you gotta think, if I'm just throwing the solid into water, there's a very specific ratio of the copper to the hydroxide. Because for every one of those, we get 2 of those. Okay? It'll get easy. It really is. This one's not that hard, it's just you gotta wrap your head around something new. Okay? They make it sound all hoo-hoo, but it's not. Fair enough? All right. Can you kill that?